This project is running with the help of the stakeholders. We have farmers that are helping us in deciding what practices we need to follow and what rates we are considering. From all the management practices that we are using for this project are actually agreed upon by this advisory group. There are farmers that are holding around 90% of acres that are being grown in Suwannee Valley. So we have a big group of farmers that are helping us in this project. All right, so I would like to thank Dr. Sidhu and Diego. Dr. Diego, can you raise your hand for running this project smoothly? All right, so we have two sites. One site is in high organic matter site. This is a high organic matter site. The cultivation history on this site is around 5 years, roughly, and it has organic matter more than 1%. This is how it looks like from the top. And we have site 2. This site has a long history of cultivation, very low organic matter, below 1. I think it's around 0.7, 0.6. And why we picked this two to have sufficient variations in among our data to replicate some of the situations that the farmers have. And this is what the picture looks like. This is our randomization that we're following along with the number of treatments. You can see at the bottom, control 0, and then 70, 140, all the way to 350, 70 pounds interval. Why we pick this higher rate? Some of the farmers are applying at that because there's a higher population, plant population. So the plant population we have had when we developed those recommendations was really low. Our recommendation around 35 to 40-year-old. And that time the plant population was not that high. Now we have a plant population of 36,000 plants per acre. Previously, the UF recommendations were built around 40 years ago. The population was from all the way 20 to 28,000 plants per acre. So that's why we need a higher number to go above and beyond to make sure that our curve is quadratic, so that it can plateau at some point to get the response curve with a better understanding. I think you have seen this picture before, but I would like to emphasize here again. So when you are planting, look at the growth stage here. So this is the curve we followed, and this is what Illinois and Iowa has done in 1970s, 80s. They divided the plant into different parts, and then they calculated the nitrogen uptake in each part of that corn. However, after that, nationwide, all the universities took the same data to determine when to apply nitrogen. But it was done in 1970s and 80s. And again, in 2021, Illinois again did this analysis, and they found that there is a 56% increase in nitrogen uptake across all plant parts. And there is a efficiency of around 65% in the plant to transport all the nitrogen to the grains. So that 65% efficiency is not from the soil, 65% is from the plant itself. So plant transport all its nitrogen to the grains, that's around 61.5. But if you apply your nitrogen here, there is no uptake, almost very small uptake required. And there are farmers that apply big starter fertilizer, 50, 55 pounds. But we started around 30 pounds at planting time. You can live with that. But once it's reached to V8 leaf stage, there's a big exponential uptake of nitrogen. It's not linear, it's exponential. So you consider applying nitrogen between V4, V6 so that it gets available. Corn is a dramatic crop. It grows quickly within days or two. You will see a two-leaf grown up. So you want to be ahead of that nitrogen application. So if you apply around between V6, I think that will be a safe zone. And then after that, you have to split all the way to R1 leaf stage. And initially, I was believing that R1 is not the stage you would need to apply any nitrogen, because I've been graduated from a Midwestern states, and there we have not a huge in-season application, big ad planting application, and it was basically assumed that by V14 leaf stage, the uptake is done. There's no need to apply after that. But here on sandy soils, I think obviously the plant behaves very differently. So we also saw that R1's leaf stage, the plant uptake still happens. So we divided our splits all the way to R1 leaf stage. These are the varieties. Pioneer 1870 are pretty common among farmers, so that's why we picked that. And this is all decided, discussed, agreed upon with the advisory group, which is our farmers. The plant population is roughly around 30,000 plants. The granular urea, we picked it because we only want to focus on nitrogen, not any other nutrient. So that's why we picked the urea. It's a hand applied. Phosphorus around 80 pounds, potassium 350 pounds. And we split that potassium into two, K-Mag and Murid, because we want to apply 60 pounds of sulfur. Make sure you all are working on multiple rate studies, nutrient management. I always call that sulfur is very important. If you do not apply sulfur and you have a sulfur deficiency, then all your major nutrients not going to perform any better. So it's not a huge requirement by the plant for sulfur, but if it's deficient, it will impact everything. We recently found a sulfur deficiency in cotton in the Panhandle area. So just to be aware. These are different splits. You can see it's 8 splits, thanks to my team who did all these 8 splits in this hot advisory Florida heat. It's a hand application. Each row was treated differently. Each row was specifically weighed out fertilizer, each bag for 8 rows. So we have 8 rows per plot, and each row has its own bag for its nitrogen rate. And you can see at the bottom the number of days we applied that. It's all the way to R1 leaf stage. These are the weighing machines we use it, and you can see Diego is applying this here. Obviously, it's a windy day, so if you are applying on the way here, it will go everywhere. So you have to bend yourself, heavy on the back, I would say. These are the sampling events we had for soil depth, 0 to 12, 12 to 24, 24 to 36. We have a gas august this year to get those samples, but in the past we were using the hand probe. We are also using the tissue sampling to learn if there is any deficiency. But on an average, around 2 weeks, depending on if the weather allows, if there is no rain, we go there and take soil and plant samples from the trials. These are some sensors we are using, and drone sensors to correlate our yield with our NDVI readings. We have hyperspectral, multispectral cameras, and we are in very good shape to publish that soon. We have lysimeters. The lysimeter is basically a device to collect all the leachate under the plot so that we can correlate with our soil sampling nitrate analysis. If there is a sufficient leachate correlation, then we'll be able to correlate with the rate that we applied with that plot. So this is how we collect the leachate from each lysimeter. The drain gauge lysimeter we installed in a control plot and a plot 280 pounds of nitrogen per acre. We have 8 different lysimeters. These are pretty heavy-duty lysimeters that are basically dug out. If I have a photo somewhere, I think I missed that, but there's a big dugout hole, and then you install that 3 feet under the soil profile, and basically you have to wait for a year to get a consistent data because you disturb the soil, so the data is not consistent in the first year. So we also bought a small research plot combine because we had a discussion with the growers, and they said, "You hand harvest." They said, "There's always a higher yield." So I was like, okay, well, I did not know how big difference could be. And very honestly, I was a little reluctant because these are expensive tools, right? But thank you to IFAS for helping us, and obviously the NFREC Suwannee Valley. They put a lot of money together, and we bought a pod combine, and we found almost 20 to 25 pound bushel difference between a hand harvest and a combine harvest. So I think our growers are right in many ways that we are hand harvest can always make more. That's how it looks like when you are using a small combine. It's air conditioned, so that's good. And we basically harvest the 2 middle rows of each plot. You can see there are 8 rows, and the middle row, 2 rows are used for harvesting. Results, the juice, right? So we have 2 sites. Site number 1 is the site that has a higher organic matter, and site number 2 is the very typical site that our farmers are using. They're very low organic matter, long history of cultivation, and you can see that. And this is a 1-year data. We are not making any recommendation, just to be sure. No impression. We're just presenting you the first year data. We do not have a second year data yet ready. The first year data tells us that in a site 1, when you have a high organic matter, the data variability is a little bit higher. So 210 and 350 are the same. There is no significant difference. And why? If you see here, standard deviation, it's pretty high in 210. And as you are on the higher end, the deviations are low, and on lower, the deviations are higher. So why is that? So some plots, basically, the plants are pushing itself to produce more. So there may be a 1 replication that is producing more than the rest of the 3 replication. We found that replication, but we didn't delete that data. If we have a second year data and we compiled with the same site, because it's pretty close to site number 1, I'm very much confident that there will be a good significant difference because you have a higher sample size, you have a degree of freedom if you know the stat, and that would reduce your standard deviation or standard error. On a site number 2, low organic matter, long history of cultivation, we found that the 280 and 350 are the best rates, but they're significant. So I would say 280 is the best rate to produce maximum corn on a long history of cultivation. But 350, it wasn't good enough. It has the same results. They are non-significant with each other. But one thing I saw that the curve is not going plateau here. So we have to extrapolate the data to figure out where the curve actually went down. So there may be a possibility that as we are adding more data, we may find 350 is the best, but at this point of time, this is the first year data. We are not saying any recommendation is ready. Okay, we also had some on-farm trials that we did. The big pivots were divided into 2 and 4. Thank you to Dusty Miller Farm and Donnell Farm. They allowed us. They obviously had a reduced yield, so they took that loss on themselves. So that's an in-kind support to University of Florida. We have 4 rates here. The 4 higher rates: 140, 210, 280, and 350, and same 2 rates higher here. We found a big dip. It was not a replicated trial, so I do not want to push a lot and press a lot on that. This year we took multiple yield data points, but it gives us some impression that the growers 350 actually had a higher yield, but we could not do any statistical analysis because it was not a replicated trial. But we're trying to understand this data and maybe discuss with our statistician how we can publish this data, or how to make sense of this kind of a data. These are the soil nitrate analysis. The arrows that you can see here are the fertilizer application events, and these are the depth rates. The different colors of these lines are the rates: 210, 280, and 350. And you can see how the surface behaves versus 12 to 24 inches versus 24 to 36 inches. So you can see that at this stage, at this depth, and at the end of the growing season, this kind of a greenish line is still have a higher nitrate availability. And that is our 350. That means after we harvest the corn, there's a leftover nitrate for in 350 rate. So that gives us an impression that whatever the nitrate was available was taken up by the plant, and what is left over is there. Site number 2, I think I did mention to you the site number 1 has a higher organic matter, site number 2 has a low organic matter, but here we also saw in the yield as well. If I go back to yield, the site number 280 and 350, there's a little difference, but there are significant differences. And here in the soil analysis on a site 2, you can see that at this depth, nothing left. Everything that we applied basically taken up by the plant. So it's a good story and a good correlation. We can make some sense from the data, from the yield, as well as from the soil nitrate. This is the plant height. And plant height is very much common in nutrient recommendation as used as one factor to guide. And we saw that 280 pounds of nitrogen has a higher, more height, not significant, but higher height, maximum height on both sides. So the height may translate into yield in many ways, but it should be used carefully. So once we have all the data from 3 years, we will compile that. This is the biomass and each part of each rate. You can see that days after planting, this is the biomass that is increasing, and 350 has a higher biomass. So for example, if we have a silage corn production, the 350 probably the best, but this is again, we haven't found any recommendation. At this point of time, we're just presenting you the preliminary data we collected. So we may be able to develop some silage corn recommendation versus grain corn. This is in different parts of plant. We analyze the plant in different parts: roots, stem, leaves, grains, cobs. So we divided that plant in different parts, and we analyze it differently to learn what's uptake in each part of the plant, so that we can make some sense how much nitrogen is moved into the grain under Florida conditions. And both have a little bit different. If you see that site 1, site 2, there is a sufficient difference in the uptake of nitrogen. And this basically goes back to the site-specific recommendation that we may need to come up with a regional or with farm management scheme-based recommendation for the growers. Extension activities, the farmers are highly involved with these activities. I would like to say thank you to FDACS, Office of Ag Water Policy, to fund this project, and NFREC Suwannee Valley staff and administration to let us do this work there, and also for their support and guidance throughout this research. I think without them, we could not have achieved what we are achieving there. Thank you.